In the world's most extreme arid environments, surface water is practically non-existent, and the relentless heat bakes the earth dry. Transporting water in the open air here is a losing battle against the atmosphere, which evaporates surface supplies long before they can reach a destination. Yet ancient civilizations built flourishing metropolises directly in the center of these zones, settlements that required massive, consistent volumes of water to survive. If you look down from above, you see the only evidence of how they did it: perfectly straight lines of circular mounds stretching across the desert floor. These are the surface vents of a Qanat, also known as a fogara or kariz, a hidden subterranean hydraulic infrastructure operating quietly below the sand. By drawing from stable, deep-seated aquifers, this underground network provided a reliable flow that functioned independently of local, unpredictable surface rainfall. This technology originated on the Iranian plateau over 3 millennia ago and was heavily refined across the Arab world during the Islamic Golden Age. These systems are precision-engineered gravity-feed extractions designed to move water from deep geological layers to the surface using nothing but the slope of the land. They also serve a second, almost hidden function, operating as a massive, passive thermodynamic heat exchanger for the architecture above. To understand how they work, first, the hydrology of the aquifer, the precision of the civil engineering, and thermodynamics of the cooling loop. What we find is a system that manipulates geology and physics to sustain cities where life should otherwise be impossible. The desert actually holds massive volumes of water, but it is typically trapped deep inside mountain aquifers and the coarse gravel of alluvial fans. To access it, engineers first have to locate the hidden water table by sinking a vertical exploratory shaft, known as a mother well. The ideal target is usually right where the slope of the alluvial fan meets the rocky mountain foothills, where the water table is closest to the surface. Once a supply is confirmed, the construction doesn't start at the mountain. The horizontal tunnel is excavated in reverse. It starts from the flat desert plain and is dug backwards, deep into the earth, toward the mother well. By digging backwards from the destination, the engineers ensure the water will naturally emerge precisely at the surface elevation of the agricultural fields. This foundational step bridges the gap between deep geological water storage and the immediate needs of human irrigation. The next challenge is moving that water over dozens of miles without a single pump, relying entirely on gravity. This requires a painstakingly exact hydraulic gradient, a downward slope of approximately 0.5%. The physics are unforgiving. If the slope is too steep, the water velocity increases exponentially, scouring the tunnel walls until the entire structure collapses. Conversely, if the slope is too shallow or completely flat, the water loses momentum. Sediment drops out of the flow, quickly building up and choking the channel. These hydrological calculations and geometric proofs were documented by 11th century Persian engineers like Qanat, who detailed the extraction of hidden waters. Executing those calculations underground meant hand-digging tunnels up to 100 kilometers long. To make this possible, vertical access shafts were spaced every 20 to 50 meters along the entire route. These shafts allowed workers to remove tons of excavated rock, hauled up to the surface in leather buckets, leaving a permanent entry point for maintenance. Crucially, spacing these shafts at regular intervals creates natural convection drafts, pulling fresh oxygen down to the excavators working deep in the suffocating darkness. Maintaining a 0.5% slope across miles of changing geology turns the Qanat into a high-stakes balancing act between fluid dynamics and human endurance. Once the water reaches the city, its function shifts from agricultural transport to urban climate control. This is achieved by pairing the subterranean water with windcatchers, specialized towers built to harness desert breezes. As we can see in this architectural cross-section, the thermodynamic loop begins when hot, dry desert air is caught by the tower and drawn down into the underground access shafts. When that 100-degree air flows over the cold, rushing water of the Qanat, it triggers a physical reaction, the transfer of latent heat of evaporation. The water pulls thermal energy out of the air, creating a dense, cooled, comfortably moist draft that naturally rises into the building's basement, dropping the ambient indoor temperature by over 15 degrees Celsius. This cooling effect is sufficient to maintain the interior of yakchals, specialized storage structures, at temperatures low enough to keep ice frozen throughout the peak of summer. Containing that temperature differential requires massive stepped domes and thick mud brick walls to isolate the cooled interior from the baking sun. In this way, the Qanat operates as the subterranean engine of a citywide, entirely passive air conditioning system. Comparing this ancient infrastructure to modern water management, a critical difference emerges: the mechanized deep well. Mechanized ponds extract water faster than rainfall recharges it, creating a cone of depression that causes permanent depletion, soil salinity, and desertification. A Qanat only intercepts the top layer of the water table. As the aquifer naturally fluctuates, its flow adjusts in perfect sync. Because it relies on gravity rather than mechanical force, the system is incapable of causing a severe drawdown. The flow is permanently throttled by the natural limits of the environment. By treating groundwater as a renewable resource, the Qanat's physical architecture prevents human extraction from destroying the aquifer. Because this system was highly sustainable, the engineering model spread rapidly during historical Islamic expansions. The technology was exported across the arid regions of North Africa, where they are known as fagaras, and into Muslim-ruled Spain. Centuries later, Spanish colonization carried these exact gravity-fed community systems, now called acequias, across the Atlantic and into the Americas. This expansion was driven by a cultural ethos that viewed water as sacred, underpinned by principles like the law of thirst, which demanded it be supplied to any living person in need. The legacy of the Qanat proves that extreme environments do not have to be overpowered. They can be navigated by aligning infrastructure with natural physical laws. As modern cities face accelerating climate crises and severe water scarcity, this 3,000-year-old subterranean technology offers a proven, highly functional blueprint for survival.